I wanted to say a couple words about, I don't. I don't think so.
We weren't ready for here, and I woke up at 6 a.m. They're all like they turn out beautiful. Those are amazing. But of course, like they weren't ready. So
Okay. I wanted to say something, let me say a couple of things here about the.
For the poor people.
wow, and it's looking pretty good today.
Just tapping out.
I feel like some email said, everybody's failing the class, maybe that would have gotten me better attendance. All right, so let's try this. I wanted to, let me say a couple of words about the next homework, and then I also want to say a couple of things about the exam as well. Okay, so this homework was assigned last week, but it's not due until next. So really, the first problem I've designed to sort of help us put a leg up on finite fields, because we're going to talk about that. Suppose that you have an irreducible polynomial over a field, and at this junction, the field can be any field, it doesn't matter. Show that there's an extension field of K in which this polynomial factors into linear factors. And we're going to talk about that actually a little bit. We actually already had talked about this. Show that the polynomial f of x has distinct roots in the extension from part A, if and only if the greatest common divisor of the polynomial and its first derivative is 1. Right? This is kind of a nifty thing, right? Yes.
Do we have an algebraic reason for why the derivative shows up here randomly, or no?
Yes, product rule.
Okay.
Right? Because, I mean, think of it this way. So this is just intuitive. You should sort out the details. But what happens if you have multiple roots? Even to the square power. So this is a root of f of x, right?
Right.
When you take the derivative of this, r is still a root.
Yeah.
Right, because you have this times q prime of x, and then when you take the derivative of this, you still have 1 power of this. And so that's essentially it. And notice that means that f of x and its derivative still have x minus r as a factor in common. So, right, I mean, you wouldn't think that the derivative, which is something that, you know, people have invented in the perspective of limits, has anything to do with it, but here we go. Consider this particular polynomial, x to the p to the n power, where p is prime, over fp, cp, if you like, the field of the elements. Show that the roots of this are all distinct. By the way, what's the derivative of this? That's right. The derivative of this is -1 since you're over field of the element. Agree? And so if f prime is -1, I bet that this GCD will be 1, right? Show that the set of roots of q of x, and if you believe part C and part B, there should be p to the n of them. Show that these form a field of p to the n of them. Compute the following Galois groups. Compute the Galois group Q alpha over Q, where alpha is this element, radical 2 plus radical 3. And compute the Galois group of the real numbers over Q. Actually, a little advanced calculus might help with part B, which I'm sure everybody is happy about. Should I worry about you since you haven't had advanced calculus? That's a joke from your topology
I
class.
know.
So actually, it turns out that that every automorphism, so if you have an automorphism of R that fixes Q, one of the consequences of this is you can actually prove that every automorphism of R that fixes Q has to be continuous, right? And once you got that, you totally nailed it down, right? So, see if you can figure out what these two animals are. Number three, this is an old chestnut that we need to go over. Suppose that we have a tower of fields, E is inside K is inside F, with F Galois over E and E Galois over K. Does it follow that F is Galois over K? Prove this yes, or give a counterexample. And finally, when we talked about in the proof of the fundamental theorem of Galois theory, we talked about priming things. You know, you prime a field, you get a group, prime group, get a field. Let FP denote the field P elements, and consider this extension here. So you have FP inside rational functions in the variable x cubed, inside rational functions in the variable x. Show that FP x cubed, this intermediate field, is a closed intermediate extension for P equals 7, but it's not for P equals 3. So just do the computation. You see that. I also wanted to say a word or two about the exam.
And closed is not like algebraic closure, that is.
Yeah, what it means to be closed is when it's equal to its double prime.
Okay.
Right, so if you start with any of these structures and you double prime it, the tendency is for it to get bigger. But when you get equality, that's what it means to be closed. So see if you can work through, I mean, I trust that you guys can get the definition. By the way, does somebody know what the answer is for number G? This is the one where you had this intermediate field E, the degree of F over K is 6 and E over K is 2. If alpha and F, then alpha is algebraic over K, hence over E. So what are the possibilities for the degree of the minimal polynomial of alpha over E?
Either 1 or 3.
Yeah, there are actually 1 or 3, because here's the way to think of this. So what you have is you have K inside E inside F, right? And the degree here is, I guess, 2, and the degree here is 6. Right? And so alpha is an element of F. Then and of course, this degree right here must be 3. Do I agree with that? So what does this mean? That means one of two things happens. Either this extension is of degree 1, in which case that means that alpha is already an E. So it's minimal polynomial degree 1, it's already an E. Or this extension is of degree 3. It's all the way up to F, in which case its minimal polynomial has to be at degree 3. Right? And let's see. This one was very similar to number 3. By the way, on number 2, see if you can get these. There should be I think there's 3 here. Yeah, so there's 3 different rational canonical forms, and here there should be 5 possible. Let me point out something though. A couple of you said it, and I kind of let this slide a little bit. So for this problem on 2, I asked you to do the, yeah, so I said various, right? I said, find all possible rational canonical forms. What if I had said find the primary rational canonical forms? There would be no difference. Every primary rational canonical form, the rational canonical and the primary rational canonical forms coincide in this particular problem. Do you know why?
X squared plus one is five.
That is right. This thing is a single prime cube, right? And so what's the difference between rational and primary rational? Well, in the rational canonical form, what you're looking at is you're looking at the invariant factors, the different possibilities there. And in the primary rational, you're looking at the different possibilities for elementary divisors. Well, there's only one prime here, and it's x squared plus one. So the invariant factors are exactly the elementary divisor. This is only true if you've got a single prime power. So this is the only case where something like this, where you've got a prime power for your, in this case, characteristic polynomial, are you going to get the primary and the rational canonical form being the same thing? And you got the same situation here. What eluded some of you is, don't forget, what does it mean for a matrix to be nilpotent with regard to its eigenvalues? They all must be zero. So this one right here must have characteristic polynomial x to the fourth. So once you realize that, it's very similar to this. Once again, you've got a single prime x to the fourth power. So the primary rational canonical forms and the rational canonical forms would all be the same. Of course, here I'm asking you to do the Jordan form, which is a little bit different, right? And the fact that you can do this is the fact that this is a linear, the characteristic polynomial is actually a linear polynomial. Am I okay with that? Number 3 is very similar. Notice that
Dr. Cordino, what is an example of for B, like 2B, what is an example that is not just zeros on the diagonal, ones on the super diagonal?
Let's put it up in like the different block sizes, like the multiplicity.
Oh,
for
I see.
example,
I see.
and there's 5 of them. There's 5 varieties. Basically, what you're doing, basically, the different canonical forms of this situation are in one-to-one correspondence with the partitions of 4. Right, so you got 4, 3, 1, 2, 2, 2, 1, 1, and then all ones.
Gotcha.
This one on number 3, so you have so in this one you have the extension is E, and you have alpha in F minus Q. Then you have this tower here. Now, this whole thing is P, right? And of course, P only has, there's only one way to factor P really. So this thing right here is 1 or P, right? But if alpha is not in Q, this eliminates the possibility of 1, which means that this has to be 1. And if this extension is of degree 1, then that means that F is all. Y'all know how to do this one now. I think I worked through actually a more general version of this in the help section or the review section, right? Basically what you have to do is show that, for example, P is not a perfect square in this ring. All right, so this is modulo some details that I probably should have written down if I was doing this problem completely. Number 4 boils down to showing that radical P is not in that thing. Which, because of the fact this is algebraic, is Q square bracket radical Q. Right? Now, of course, it seems obvious, right? But suppose that you have radical P is A plus B radical Q. Well, there's something to prove, because if you square both sides, you get P is A squared plus Q B squared plus 2AB radical Q. Now, by the linear independence of 1 and radical Q in this field, this means that this has to be 0. So either A is 0, which implies that and from here you can get a contradiction out of this. Remember, B is rational. Yes.
How is the 2AB 0 again?
Right, because in here, 1 and radical Q is a basis. Right. So another way to think of this equation is you can think of this way. 0 is equal to negative P plus A squared plus QB squared plus 2AB radical Q. This is a linear combination of the basis. This times 1, this time radical Q times this, right? Equals 0. But since they're linearly independent, that means that both of these have to be 0, right? And that's where the 2AB is 0. Here, this would be easy if B is an integer, because that would mean that Q divides P, which is ridiculous, right? So that would force B to be 1 and P Q, which is a contradiction. It's a little more lengthy because this can be a rational number, so you have to do out the denominator. But we went through this, and B equals 0 gives you something similar. You get A squared equals P. Again, this can be a rational number. Clear the denominators and get a contradiction. Right. So that's essentially the gist of this. And finally, a lot of people actually almost everybody got the first part. Well, there's actually a whole bunch of answers to the first part, but one of the answers is this: fx, right? The polynomial ring. That certainly contains f and is contained in the rational functions, and there's stuff in there that's not a variable like x, right? Let p of x be any non-constant rational function. I would have been okay with you saying, okay, since p of x is non-constant in a rational function, it too is transcendental over f, just like x is. And we have a theorem from class that says if Bill and Fred are transcendental, then f adjoint of Bill and f adjoint of Fred, and then you're good. Some people, like you, Megan, in particular, I think you actually did the homomorphism, which that's okay too, right? So that worked. You kind of got it by discovery. A lot of people said, okay, so these are isomorphic. And so somehow you came to the conclusion that the degree of this extension was 1. There were a lot of people that said, okay, the degree of this extension is 1, therefore it has to be algebraic, right? Well, first of all, it's not necessarily 1. For example, let me have p of x equal x to the n, right? Then this extension is of degree n, right? And I can make this anything, right? Just by varying what n is there, right? So how do you do this? Well, let's do this. You're gonna think I'm just a big fat cheater, but I'm okay with that. Write your rational function this way. Now, look at P of X times, okay, just take what this polynomial is, the B, and instead of X's, write T's in it. Okay, this is a polynomial with coefficients with variable T and coefficients in F, right? Anybody agree with that? And this is a polynomial with coefficients in F, and variable T. Now, when you multiply this through, whatever this is, this will be P of X times every coefficient T here. So now this whole polynomial is, all the coefficients in here are in rational functions of P of X, right? Everybody agree with that? Because every coefficient here is P of X times something in the field, which is still in F P of X. And every coefficient here is in F, which is even more restricted. Now, plug in X. Plug in X for T, I have P of X times B of X minus A of X. And that's going to be A of X over B of X plus B of X minus A of X, which is, so it's algebraic. Yes.
So technically, F square bracket X is not contained in F circle bracket P of X, right? Like we don't know that at the outset
You don't know what at the outset that.
that F square brackets X is contained F circle brackets P of X.
Oh yeah, there's in fact it's often not.
Mhm.
Right, depending on what this is.
Right.
Right.
And so we're just saying that like, you know, F circle brackets X is gonna be like an extension of F circle brackets P of X, right?
That's correct.
And so we're just like harkening back
Right.
to F square brackets X.
Right.
How does it show like for all at like what if there's a U and that's like not a root? Like how do we know that F like for all elements in F adjoint X is a root of
Okay, yeah. Here's why. Because, okay, so now I'm on your page. Okay, what we showed is X is algebraic, right? But this thing is, I mean, this is like super redundant. Right? Because that's all you need to get all of this. Right? Let me also point out that there are, here, let me give you an example just to make you angry. So, given the answers that I got also, I think I should do this. Consider any field. Consider rational functions and calibrating variables. X1, X2, etc. So what this is you've got infinitely many variables. This has xi in it for every I. but any particular rational function only uses finite many of the variables, right? I mean, you don't have x1 plus x2 plus x3 forever. Any fixed rational function only uses finitely many. There's infinitely many to use. This is actually isomorphic too. Just add one more variable, just to make yourself, to anger up the blood. Can anybody describe how this isomorphism might work?
You just associate y with x1 and every x1.
It's a Hilbert Hotel thing. That's exactly what you could do. You can actually use, so what you can do is if you think of this as polynomials first, what you can do is you can associate x1 with y. And then to shift all x2 goes to x1, x3 goes to x2, and so forth and so on. And that will give you an isomorphism of the polynomial rings, and therefore their quotient fields, which is this, the isomorphism.
So that only works out if it's infinite, like if the x's are infinite.
That's right, that's right, that's right. But this is what should make you angry. Call this K is isomorphic to, call this one L. K is isomorphic to L, but L is actually transcendental over K and is infinite degree over this, right? So this is, you can get bad things to happen. Yes.
But for that specific, like having the degree of the extension be infinite, you don't need necessarily all of this, right? You can just do f adjoint s.
Oh, yeah. So you can have f inside of fx, and that the degree of that will be infinite, right? But f and fx are not isomorphic.
Right.
Right. So, I mean, this extension is transcendental. It's transcendental. It's infinite dimension. Well, of course, it's transcendental. It has to be infinite over this. But they're isomorphic, which is, part of the weird games you can play if you got infinite things.
All the x's or like all the roots in K or in L are also in K except Y. Is that what like adjoining Y is?
Well, really, I mean, so here's essentially what it is. And in fact, what I told you just a moment ago, you got to be careful about. Whoops, I'm sorry, L. You can visualize this way. So in the special case, I just said that, f and fx are not isomorphic. Is what I said. That's not always necessarily true. It certainly is in this case because L is K is big enough to make this true, right? In the circumstance. But the isomorphism. So K is isomorphic to KY, but the difference is, if you look back when we talked about, the difference is this. The isomorphism, if there is the isomorphism here, does not fix K, right? Because what happened with the K is I had to shift one of these guys outside of K to cover the Y, right? So that's the difference. I mean, usually when you think of F inside FX, you just think of embedding it, right? There is an isomorphism here, but it's because K is so big, and this isomorphism does not fix K, right? So.
Dr. Codenberg?
Mhm.
If you have f circle bracket x comma y, that is isomorphic to f circle bracket x circle bracket y, right?
Let me write this down. F. Oh, I see.
but they're not contained in one another.
Oh, no, these should be the same. Yeah, I mean, yeah, because, I mean, if you have a rational function in x, y,
Right.
you can obtain that as a rational, you can pull that apart,
Yeah.
right? So,
Are they the exact same?
yeah, because, so, let's see, which is, all right, so we'll go through the details on this. Okay, so if you really wanna be pedantic and pick this apart, it's not a bad idea. An element of fxy, let's say that, A is in f x y. Well, okay, I'm gonna treat this like a rational function in the variable y. So this is, R1 y.
Where all the coefficients of R1 are radical functions.
Yeah, so let's write this way. This should be a rational function, so it should be a0 plus a1y plus a(n) yn over b0 plus b1y plus bm ym, right? Where the ai's and the bj's are rational functions in x. Right? And so this is, let's say, P0 x over P1 x plus, what do we call that, prime, P1 x over P2 x y plus P in x over P in prime x y in Q0 x Q0 prime x Q1 x Q1 prime x y plus Qn x over Qn prime x y to the n. And is it clear now that if I multiply by, in fact, I can multiply by the product of all these denominators that I see, and what I'm going to get is a polynomial on xy divided by a polynomial on xy.
But what exactly do you multiply with?
P0 prime, P1 prime, Pn prime,
Sure.
all times Q0 prime, Q1 prime, etc. So clear all the denominators. And then what you're going to have when you clear the denominators is polynomials in x and y. Right?
Wait, are you multiplying by P0 prime over Q0 prime?
No, I would multiply P0 prime, P1 prime, Pn prime, Q0 prime, up to Qm prime x. And what that'll do, I've got a factor for every denominator that I ever need. And it's gonna leave me with a huge product of polynomials. So what I'm gonna get is, I'm gonna get a polynomial in xy over a polynomial in xy. So in particular, anything in here is in here.
Isn't that, shouldn't you be dividing by all of the Q primes?
I multiply top and bottom by this.
Oh, okay, gotcha.
And so, and if on the other hand, you have if you have a polynomial in xy, right, then so here, if you start with a polynomial in xy, then take all the x terms, then y times all the x terms. So what you can do is, if you have pxy, you can write this as, you need to organize this. So take all the terms that have no y in them and call that a0x. Now take everything in here that have exactly one y.
Does that imply this depends on choice?
No, it's a finite process.
Okay.
This is yn. Because it'll be a highest power of y.
Right, yeah.
Do the same thing down here. Right, and this is even easier because this is a rational function. This is a rational function in y, and we've actually, the way we've written it, this is actually in fx, rational function y.
Because it's transcend level.
Well, right, so actually, when I take the field, that should be this. Yeah, because of the bird stuff. Yeah, because actually, I've written this in the simpler form, and in fact, the form that I have written there at the outset is the form I would get once I reduce this, right, and multiply top and bottom of the denominators. So these two things are the same. Okay, any questions on it? Yes.
So is that the degree extension? Is that 0? If they're the same, is it extension
If they're the same, the extension degree is 1.
1?
Yeah. Okay. Okay. Other questions? All right, might have time for. Believe. All right. So the last thing that we had was we had this business where we defined what it means to be stable. We defined an extendable thing, and the last thing we had was the limit that we're talking about. Real quick. So this was lemma 14.2.14. If E is stable, then E prime, which is the Galois group of F over E, is normal in Galois group of F over K. And 2, if H is a normal subgroup, okay, then H prime is a stable intermediate extension. So this is the one we had last time. Let's try to prove this. Okay, so we've got that E is stable. So this means that sigma E is contained in E for all sigma in the Galois. I want to show that it's normal, right? Well, so to this end, let's let sigma be in the Galois group of F over K and tornado in the Galois group of F over E. And we're trying to show, of course, that this is normal, so, we need to show that, sigma inverse tornado sigma, is in the Galois group of F over E. Right. That is our goal, show this normality. Well, notice that as tornado is in the Galois group of F over E, tornado E equals E for all E and E. Right, it fixes that. So let's see what happens. If you look at sigma inverse tornado sigma of E, what happens here? Well, I know that it's stable, so I know that this chunk right here is in E. Everybody agree with that? So that means that this, right, because tornado leaves everything that's in E alone. So this thing becomes sigma inverse sigma E, which is E. Therefore, the Galois group of F over E, because it fixes everything in E. Therefore, the Galois group of F over E is normal in Galois group of F. Any questions on that? Now we're going to kind of do the backdoor thing, come from the other direction. I want to show that if this is normal, then H prime is stable. Okay. Now suppose H is normal in the Galois group of F over K. Notice that we recall H prime is the set of V in F, such that sigma V is equal to V for all sigma in H. Right? And what do we know? We know that this is, well, we're trying to show that this is stable. So let's let I should have thought about notation a little better for us. So now let's let tornado be a general element of Galois. Okay. And we need to show that tornado V is in H prime for all V and H prime. And we need to use normality. So it suffices to show I wanna show that this guy lives in, H prime. And what does it mean to, live in H, prime? It means that, it's left alone by everything here. So it suffices to show that sigma tornado, B is equal to sigma, B. Wrong, didn't I? Check up the stomach a little bit. So we need to show that, for all sigma, so we'll let sigma be an H. We need to show that, sigma tornado. Right. For all sigma in H, that sigma tornado B plus tornado B. Okay, I don't know why this is. This suffices to show that, right? Because we need to show that this, because tornado B is still in H prime, right? And this is what, but notice that this is equivalent to that. Correct? Yeah. But this holds as H is normal in Galois. Okay. I'm gonna leave you with this last lemma and then we'll call it a day. We'll talk about the proof next time. But what we're doing is, we've got the last little bits of flotsam and jetsam that we need here to finish the fundamental theorem of Galois theory. The last theorem says if F is Galois over K and E is a stable intermediate extension, with F Galois over K and E stable, then E is Galois over K. And that'll do it for today. Any questions?
Dr. Gordon,
Mhm.
do we already have that, if E is stable, is a stable intermediate field, then, E delta prime is equal to E?
Let's see. Didn't we have something about the closed fields or stable? Yeah.
The stable is like closed?
Let's see, we've been at that yet,
Yes.
Yeah.
After.
okay. Okay, anything else? All right, we will see you folks, have a good weekend, we'll see you on